Hello, can you hear me?
Yes, yes, sir. I can hear.
Okay, so we are starting now in I think about a minute. Is the recording on?
Okay. Yeah, recording and live streaming both are on.
Okay, nice. So, welcome everyone to the second day of the workshop about arm exploitation. Today, the title is Advanced Arm Exploitation, and today we are going to start with practical exploitation on arm. So, let's start. If you have any questions during the session, please do not hesitate to ask. I would really love to attend your questions and to clear your doubts. Uh, Ravi sir would not be able to join us today because he is ill. So today's session will be led by me. He will join us probably in the midstream, but he would not be able to speak because he is uh, not well today, right? So about me again, my name is Himanshu Khokhar. I am an independent security researcher. I am a speaker, instructor. I've been speaking at conferences, local events, meetups for some time now. And my favorite topics are exploit development, malwares, rootkits, reverse engineering, probably anything which is which has to do anything with machines, low level, right? If you want to connect with me, you can connect with me on Twitter, where my handle Ponrep. So let's start. Now, this is the today's agenda. Today we are going to cover a few topics. The first thing we are starting with the memory corruption. So, for those who are not familiar with the topic of memory corruption, they will also, we are making sure that they also get to understand what memory corruption is, how it works, and how it is abused to take so that we take advantage and get shell on the system, right? Then, followed by that, will be taxonomy of vulnerabilities. In the second topic, we are going to discuss different vulnerability classes, how they are different from one another, what are the key features of a particular vulnerability class. Then, once we have a general idea about different types of vulnerabilities, then we are going to start with buffer overflow. Now, here we are going to cover a little bit of theory, followed by a little bit of practical about what goes behind the scenes when a buffer corrupts, or what do we actually mean by memory corruption or buffer overflow in this context. Followed by that, we are going to cover buffer overflow exploitation, right? So, in the fourth point, we are going to write an exploit for the buffer overflow vulnerability. We will perform every single step, starting from the very basic of crashing the application, then analyzing it in debugger, trying to control the PC, and then after that, followed by shellcode injection and getting the shellcode executed. In the fifth, in the fifth topic, we are going to cover format string exploitation. We will see what format strings are if you have a program in C or C++. Though format strings are also a part of Python, Java, but they are not that much used as they are used in C, C++, or alike, right? Now, if you have used printf, you have used format strings in your program, right? We are going to see what actually a format string is, how it can make your programs vulnerable if you are not handling it properly, as well as if a program is handling vulnerable format strings. So how you are going to exploit it. Now, in the format string exploitation section, have a we are going to have emphasis on two topics majorly. One would be to be able to read arbitrary memory, which can be termed as out of bound read, but that is kind of different class of vulnerability. Then the second thing that we are going to focus in the format string exploitation section is uh, the ability to write whatever we want to wherever we want, which is basically called a write what where vulnerability. And then we will be following format string exploitation with dep, bypass, and drop. We are going to discuss what dep is and what drop is and how to bypass dep with drop. So if you are not familiar with the section, there is no need to worry. We are going to cover every single thing in quite detail. And of course, again, if you do not understand something, please ask so that we can make sure that while you're attending the session, it is productive for you as well as us. Okay, so starting the session with introduction to memory corruption. Now, as per Wikipedia, memory corruption occurs in a program, whatever. See, memory corruption on a very simple scale or on in a very simple language is when memory contents of a location are corrupted because of any action which was not supposed to do it. For example, let's suppose you are modifying the contents of memory location 3, but but the content of memory location 4 is also changed as an effect of your action. So that is an example of memory corruption. Now, usually what happens is when a software encounters memory corruption, the program crashes. The reason for that is there are some important memory locations which are used to control the execution path of the process. Now, what happens if you change the execution path? Now, if the execution path changes, the program will not know where to go. Well, it will know where to go, but since it is an indirect effect of the memory corruption bug, it will be an invalid memory address. And since the memory address will be invalid, the program will crash because
हाँ
there
बोलो.
is not going to be any instructions at that address. Now, in some cases, it can be leveraged to control execution of the program, but it is not always the case. In some cases, you would be just able to crash the program, but in other cases, you would be able to control the execution. So the whole okay, so the whole purpose of this workshop is to see how to convert a memory corruption bug into the ability to control the execution of the program process. So let's see how it works. Okay, starting with the taxonomy of vulnerabilities. Software bugs come in many shapes and sizes, and there are different flavors too. For example, there can be variations in size and the vulnerability access or the bug triggering in the similar vulnerability class or the same vulnerability class, but by different flavor, I mean different vulnerability classes. So most common bugs are usually buffer overflows, which come in two different flavors. One is stack-based buffer overflow, and another is heap-based buffer overflow. Now, what you have to understand is in both of the scenarios, the bugs are caused by an unbound write to memory, which is why the category is buffer overflows. But the distinction is whether the buffer which is being overwritten is present on stack, which is usually the case with local variables, or it is in heap, which is usually the case when you allocate dynamic memory using malloc, calloc, reloc in C, C++, or some other languages where you dynamically allocate memory, right? Now, another class is uninitialized variable exploitation. In this scenario, there is an uninitialized variable and that is used without being initialized. On the surface, it does not seem bad, but if the underlying content or the underlying memory locations have been compromised or have been planned out properly by the attacker, then the uninitialized variable would contain attacker controlled values, which then can be used to exploit the binary. Now, of course, it depends how the variable is being used. If it is just being used to add two numbers and then that is printed on screen, then that is a different scenario that would not be exploited. But if the uninitialized variable is a function pointer or something else, then that can be used to control the execution of the program. One another class is use after free bugs. Now, if you have, you might have heard about use after free bugs because these have been a lot in discussions, particularly regarding browsers. So, use after free bugs, as the name says, the memory is used after it has been freed. So, consider this: you allocated a block of dynamic memory using malloc, let's say, and then you did some operation on it. Then what happens is once the use for that variable or memory block is done, you free that memory, right? Use by calling the free function on it. Now after that, you accidentally use the same memory block for other operations by controlling sorry, by controlling the heap layout. It can be exploited to gain control, execution control. Another class is forward string bugs, which we are going to see today. We are going to exploit forward string bugs. So forward string bugs, as I said, are introduced because of improper usage of forward strings in functions which expect forward strings. For example, the printf family, printf, s printf, sm printf, v printf, vn printf, I guess, vf printf. So there are multiple functions which use forward strings. Now after that, there are command injection bugs. Now, command injection bugs, if you are familiar with web applications, you might have encountered command injection bugs in your own findings or during your assessments. Now, command injection bugs may be present, for example, in routers where there is a web application interface, which can let you introduce a command as the function expects it as an input. Integer overflows are another concern. So there are boundary issues, signed, unsigned. Some functions expect unsigned input. So when they get a negative number or a signed input, they will simply convert it to a positive number, which gets converted as a very big number. And then based on the different conditions, it can be exploited to gain code execution. Any doubts still here? Oh, sorry, I forgot to share the link. Yeah. So these are the slides. Now, how do we accidentally use the same memory block in UF? Say in a very small program, when you only have one or two dynamically allocated memory blocks, then it is not that hard to not use it, right? I mean, you can simply see that you have freed the program, freed the memory block. But when you have a very big project and there are tens of twenties of 20 people working on the same project but different modules, then and at the same time the program or the process is using a lot of different types of virtual dynamic memory, then it becomes quite hard to keep track of virtual memory blocks which have been freed or which have not been freed. Okay, can you show a live demo of? I cannot show the live demo of UF today because use after free. I can show a demo, but exploitation of a UF depends. So we do not have enough time to cover any heap based topics. Though I originally planned to cover heap, but I do not think there is enough time today because one of our host is ill, unfortunately. So let's proceed. Any other doubts till here? Okay, cool. Now we are moving ahead. Introduction to how to fix it. Okay, so introduction to buffer overflows. A buffer overflow is a bug which occurs when you are able to write data to adjacent memory locations when you are not supposed to do it. For example, a program takes your name as an input, and let's suppose it only has a space of 20 bytes to store your name, but it does not perform proper checks whether the input size is 20 or more. Now, if the input size is more than 20 and the function or the program is not checking properly, then what happens is you might be able to overwrite the adjacent memory locations by the remaining size of the input. For example, let's suppose your input size is 24 bytes, but the memory location or the input array has only 20 bytes of space. So what will happen to the remaining 4 bytes? Essentially, they will be get written after those 20 bytes, 4 bytes in the nearby memory locations. One of the most common, so buffer overflows are probably the most common or the most exploited memory corruption bugs out there. Though it has been changing because of various different memory exploit mitigations. We are going to have a look at different exploit mitigations. The first research on exploitation of buffer overflows was published by LF1 in 1996, and the title of the paper was exploiting, I think it was exploiting buffer overflows for fun and profit. Now it is okay. So with that covered, let's move ahead. This is how it visually looks like. For example, this is the buffer, as I said in the example that there are about, let's say there are 20 bytes available for our input, right? So this is the buffer for that. Then there's the base pointer. Then there is a return pointer to the function which hold this particular function. And then there are other stuff on the stack. Now, if the size of the input is enough to uh, stay or stored inside this buffer, then it is nice. But if your buffer, if your input is bigger than the size of the
चल चल बुला उसको तब आते हैं
buffer allocated for your input, then it will definitely go into other places. For example, it will override the base pointer, and eventually, if you write far enough, it will override the return function pointer. So, is that clear, or are there any doubts in this section? Yeah, nice. So, uh, moving ahead, let's have a little demo of how it all works and how stack corruption happens, right? So this is the Azeria Lab VM, which you'd have downloaded from yesterday for the yesterday's session and today's session. Let's start. So I am SSHing into my ARM, ARM emulation, and 68.0. kind of group are you asking for? Okay, so let's write a very simple program. Let's just write function 3. लिंक कहाँ से मिलेगा क्लास का? This class is live. It is not going to be done again. So okay, so let's see this thing. Yeah, we are just writing a small program. Okay, so this is a very simple program. All it does is the main function. It calls the function one. It calls function one. Function one prints function one, and it calls function two. Function two prints function two, and it calls function three, and function three just prints function three, right? Any questions in this program? So what we are going to demonstrate here is what how the program or how the process keeps track of where it is and how it returns from the function to the function where which called the current function. So let's just say let's just have a little input as well. So okay, a simple buffer of 4 bytes inside. Let's put it inside the function one so that we can see. It's a 4 byte buffer. We are using the gets function. The gets function, it does not control how many bytes it will take as input. Right, as you can see, we have not passed any number or any number of bytes which will, yeah, okay, so I will increase the size. Is it okay? Or I think, should I increase it a little more? Okay, cool. So as the gets function does not take any size argument, it just takes the address where the input will get stored. You can see where we are going to with this, right? So let's just do this, compile it again, uses it, and run it. Now this is the output. Now this output is pretty expected. For example, the main function prints the main and then it calls function one. So the function one prints function one and it calls function two. Once it calls function two will print function two and then it will call function three, which will then print function three. And then it will come down here, it will take input, and then since nothing is going to happen after the input, so we just simply exit. And this is what we see right here. Now let's see how it looks like in assembly so that we can have an understanding of. But first let's see, we will see how that works. But what happens if we increase the input size? For example, let's say, and the program crashes, which it was not supposed to do because the input size is much bigger than what is expected here. Now it only has 4 bytes of space, but here I wrote 8 bytes, and therefore the program crashes. Now let's investigate. So let's load in the GDB, type GDB program name and dash q minus q. Yeah. So it takes a bit of time to load. What is canary? We will come to canary when we are talking about canary, but it is a little too early for canary, right? First, you have to understand why the canary is used. Then, okay, so let's have a look at functions. So type the command info functions to list all the functions. Okay, nice. So we can see multiple functions which we do not remember, but here are the functions that we remember writing. One is main, one is function one, function two, function three, and then there are some other functions. Okay, as for the questions, I compiled with canary, right? So, well, buffer overflow can happen, buffer overflow will happen, and buffer overflow is happening right here. We will see how that works, right? Can you use IDA for this? Yes, you can use IDA for this, but since GDB is by default installed on the machine, you have to take the binary outside. If you're comfortable with that, then yes, please use IDA Pro. Thank you. So let's disassemble. To disassemble a function or to see the disassembly, let's just sorry. Disassemble main. And this is the disassembly for main, and you can see here this is a call to function one. It is a call to puts. It is a call to function one. Now, if we disassemble function one, we see there's a call to function two right here and a call to gets. And then this after that, this is the return part where the function ends and returns to the caller. So let's set up a breakpoint here. Now let's disassemble the remaining functions as well. Function 2 and same goes with function 3. Now all the functions have a starting part which is function prologue, which sets up the frame for the function, and then there is function epilogue which kind of destroys the stack frame or any space reserved here, so it resizes the stack frame again and then returns to the caller. So this instruction is a part of function epilogue which is executed when the function ends, right? And you can see this in every other function. For example, in function 1 it is right here, in function 2 it is here, in function 3 it is here. Now let's have a little look here. So main calls function 1, function 1 calls function 2, and function 2 calls function 3. So this is the organization of our program. Now when this ends, of course, when the function 3 ends, it will just return the control to function 2, which will then end return to function 1, and then it goes to main. So let's place the breakpoint on the last instructions. So we use the command b for the breakpoint, star with the function name function 3 plus line number. So this is plus 16. So plus 16. We have one breakpoint right here. One breakpoint we are going to use at we are going to put at function 2 plus 20. And one we are going to put at function 1 plus this is function 1 and this is the instruction plus 34. Okay, so now we are going to run this program. And we hit the breakpoint, right? So there is this breakpoint 1. And you see at breakpoint 1, this is where the breakpoint is. As you can confirm it, yeah, so the PC is 48. And here we go, right? So pop R7 PC. Now if we see what PC is, so R7 will be this value and PC will contain this value, which points to function 2 now, right? Let's disassemble at this. Let's disassemble at this address, disassemble, and we can see that this, yeah, so this is where 62 knob is, just after call to function 3 in function 2. This is located on the stack. This is the top of the stack. If you see the stack pointer points to F5B0, which is the same, right? So top of the stack contains one value, which is going to be popped into R7, and the second value, which will be popped into PC, and PC is the program counter. So sorry. So once I do a step by instruction or execute a single instruction and then stop, we will end into function 2, right? You can see we are into the knob just after the call of function 3. And if we disassemble it again, we see we are right here after the call to function 3 because function 3 has done executing. Now SI was instruction And here we are at the second breakpoint, which is at the end of the function 2. And again, top of the stack contains a value, and the second value on the top on the stack is, which is going to be restored in PC, is this value, and it is function 1 plus 21 as the debugger helps us, right? Let's just do an SI, and here we go. It says function 1 plus 21. Now, if you disassemble it, here we are. Now, what difference you can see here is it says 81, but it says 80, but the instructions are same. Now, the reason for that is it the processor is currently in the thumb mode, right? You can see the instruction sizes are 2 bytes, CE02468, as opposed to ARM mode where the instruction sizes are fixed 4 bytes. And in thumb mode, since one is added because of how it works, right? To signify that it is in the thumb mode. It is why this is why the debugger is like this. It is pointing to wrong address. It is trying to fix the address when it should not be trying to fix the address, because we are already having proper address, right? 80, 81, but the instructions are same. Now that thing might irritate you a little bit, but do not get discouraged with this, right? Now uh, if we move ahead, right, if we execute some more instructions, what we're going to see is this. There's a call to gets function, and this gets function is the same gets function is the function which takes input in a function 1, right? We just wrote the code. Now let's continue this, and 3 4. Now after this, we are at a third breakpoint, which is the last statement of, or the function epilogue of function 1. Now, since we are at the function epilogue, the top of the stack value will be popped into R7, and the second value, which points to main plus 19, which is main plus 18, I think, and will be popped into PC. If we do an SI, we get into the main function, right? Just after function call to function 1. And if we continue, the process exits, right? Now this is how the stack is arranged: main, function 1, function 2, function 3. And in this scene, we have seen how PC is used to maintain execution control. Okay, so let's see some questions. Which architecture is this? It is ARM architecture. The whole workshop is ARM exploitation. So yes, this is ARM architecture. Now, what is a stack? I don't understand it properly. A stack is a data structure which is used for different operations. In the current context of a process management, a stack is used to save runtime information, usually, such as local variables, stack pointer, so that different nested calls can happen, as we saw. Main calls function 1, function 1 calls function 2, function 2 calls function 3. Now, stack is used to save the program counter, so that when function 3 ends, it knows that it was called by function 2, so it moves back to function 2, and then function 2 was called by function 1, so function 1 is called back, or it returns to function 1. And then at the end, we are back to main function. Branch expedition. If it is required for the training, I will. But if not, then I guess I will not be able to because we do not have enough time. Global variables are stored in data section or BSS section, it depends. How to find bugs in stack in real application. There are no bugs in stack as such, but I think you are asking for how to you are asking how to find stack buffer overflows. So you do fuzzing. So are you familiar with fuzzing? Anyways, I think we are getting out of control here. So let's move back to the uh, presentation. Okay, so the demo is about visualizing stack corruption. Now, when we have seen how stack maintains, how stack keeps track of program state, let's see how a big input, for example, let's just run the program similarly. Let's quit it. And now if we give it an input of 3 or 4 bytes, nothing wrong happens, right? Let's see the program code. We see that we only have a space for 4 bytes. Now, if the space is there for only 4 bytes and we are giving it 4 bytes, then of course there will be no crash, right? That is expected behavior. But what happens if we put or if we try to store more than 4 bytes of data? So let's see if what happens if we try to store 8 bytes into it and the program crashes. Let's see the reason for this. So load the program again in GDB. Oh, sorry. How to remove corruption? How to remove corruption? I don't understand the question. Okay, so let's just, since our input is in function one, let's disassemble function one. And here is the call to gets. Now this gets function is the function which is taking input. So let's put a breakpoint here at function 1 plus 24. Break function 1 plus 24. And let's run this thing. All the printing will come before this thing, so no need to worry about anything. And now we are waiting at our breakpoint, which is gets. Let's see how gets take arguments. Now gets take a single parameter, which is a pointer to address. Okay, somebody is trying something. Okay, so as we know from yesterday, the arguments are passed in registers in ARM. And since arguments are passed in ARM, in registers, the first argument is passed in register R0. Therefore, the only argument that gets take, which is the address of buffer, will be passed in R0. And at this point, let's see what R0 contains. This is the address. Let's dump memory from this R0. So let's say 12 words in hex from this. And we see this. Now you might recognize this. Let's see what this is. This seems familiar. And Let's disassemble it. And it is main functions A7, which is here, right? A6, because 1 is the least significant bit is used to tell that we are in the thumb mode. So the actual address is 5A6, which is just after the, which is the return address for function 1 address, right? Now, this is the saved frame pointer, or basically R7, which we see if we disassemble function 1. We see this is this value is the return address for the PC. For this, the R7 will be this one. So we only have this address, or basically these 4 bytes for input. But since we only have 4 bytes, and if we overwrite 8 bytes, we will overwrite these 4 and these 4 as well. Let's write 7 bytes. 1, 2, 3, 4, 5, 6, 7. And there we go. Now let's dump the data again from this address, I think 5E4. And this is 31, 32, 33, 34, 35, 36, 37. Let's just print it as a string so that we can see it much better. This is the input that we provided, right? Now this input is 7 bytes plus a null byte. So there are 8 bytes, 1, 2, 3, 4, 5, 6, 7. And then a string is terminated by a null character. But what happens if we input more than 7 bytes? Because one additional null byte will be written by the program automatically. So let's say we write 4 bytes. Sorry, we write 8 bytes and then 4 bytes after those 8 bytes. So let's run this program again. So by running the program again, it will start again. Let's dump the data. This is the stack right now, or this is actually the address of the buffer. Now let's write 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 bytes. So the first 4 byte 1, 2, 3, 4 will go here. 5, 6, 7, 8 will go here. This is what we are going to overwrite because this is the PC, right? 1, 2, 3, 4. Let's add 4 B's and let's add 4 C's. So it will be written by B's and then it will be written by C's. Let's do this. And now when I dump this, you can see this. It is the same as previous one. These are the 4 B's, 42, 42, 42, 42. These are 4 C's. You can see 43, right? And then the last one is a null byte after our input. Any doubts till here? This is the input that we entered. Okay, so we are moving ahead. And if, okay, let's disassemble so as to see where we stand right now. So this, and then this would be the last instruction. Let's do SI for a single instruction, single instruction, single instruction. And now this is the instruction that will get executed, and the debugger says cannot disassemble from PC. Let's see SI, and it says cannot access memory at address 424244, which was basically what we wanted. Or if I say in better terms, this is what happens when memory corruption happens. So let's uh, dump the memory again. Now we can see that we only had 4 bytes to store our data, but because the input was unchecked, we were able to take more than, we were able to input more than 4 bytes of data. And since we were able to input more than 4 bytes of data, we overwrote adjacent memory locations. And of course, if you input more than, let's say 16 bytes, you will also overwrite these locations, right? But the whole point is, this is how stack is corrupted by unchecked data. So let's move ahead with a presentation. Here we go. Now let's talk about exploit mitigation techniques on Linux. Now, as exploitation became more and more common since it started somewhere around late 1990s or early 1990s, it was expected that developers will use some kind of mitigation techniques to either shut it down, the vulnerability class, so that nobody can exploit a particular vulnerability class, or to make it harder to exploit, for so that it becomes quite harder uh, as compared to the actual output of the exploitation, and therefore people will not choose to exploit these things. So some of the most common exploit mitigation techniques are SSV or stack canaries. Now, what this exploit mitigation technique does is it places a random value before the return address. So, okay. I think we have gotten quite far away. Yeah, here we are. Okay, so coming back to our demo, this was the return address, and since we were able to overflow the buffer, we were able to override the return address. Now, what SSP does, or the stack canary does, is it places a random value, let's say here, not exactly here, but anywhere before the return address, right? So let's suppose this is the buffer and this is the return address. So let's suppose this is the canary. So if the canary is a random value, what happens is, before this instruction, there is a check to see whether this canary has been modified or not. Now, if this canary can only be modified by a buffer overflow. The reason being, the program does not modify the canary, and if you are writing from here to here, you are bound to overwrite this thing. And since it has been modified, the program will see that something has modified the canary and therefore potentially modified the return address as well, which will then terminate the program. This is how stack canaries are used as a mitigation to stack overflow. Another mitigation that you might have heard about is ASLR, or address space layout randomization. What this does is it changes the memory mappings randomly on each execution, so that you do not have a predictable address. You do not know which address or which memory location will contain what at next execution, and therefore you cannot hard code any memory addresses, so that you can return to during your execution. Now, next one is dep or NX, or how it is said, XN on ARM devices. Now, dep stands for disable data execution prevention actually. NX is no execute, XN is again execute never. These are all are pretty much the same thing. And what they do is they disable code execution from memory, which is not marked as executable. Now, when memory is not marked as executable, your shell code will not get executed, because your shell code is always a part of the input And since input is read by the program at runtime, so it is either placed in stack, on the stack, or in heap. And since neither the stack nor the heap is executable now, well, you cannot execute it. And therefore, even if you are able to control the return pointer, you will not be able to execute your shell code. Another one is rel-row, which is relocation read only. Now, it works in conjunction with dynamically linked binaries. So what happens is, when your binary is compiled as a dynamically linked binary, which is by default usually the case, the functions are not resolved until they are needed at runtime. So let's suppose you have 40 functions in your binary, but during execution you only need 4. So the remaining 36 will not be resolved. But this poses a problem because since the functions are resolved at runtime, what happens is uh, they are their runtime addresses are stored in the GOT, or the global offset table. And if the attacker manages to overwrite the global offset table, they will be able to control the execution of the program. So what rel-row does is it resolves all the dynamic symbols before execution of the binary and marks the GOT as non-writable. So now the GOT is non-writable and you cannot write to it or modify it to get code execution. Another common exploit mitigation technique which is on the rise these days is Pi. So Pi is position independent executable, which makes the whole executable or whole binary as position independent. Or basically now all the sections are relative to each other instead of being some sections being absolute in their addressing and some being relative. So with that understanding, okay, any questions for now? Okay, great. So we are moving ahead to practical buffer overflow exploitation. So as we saw, we can overwrite memory location with the data of our choice. Since PC or the program counter is saved on the stack during function calls, we can overwrite it through buffer overflow, as we have actually seen, right? But the only problem is PC must point to a valid area in memory or the process will crash. So let's have a little demo of overwriting saved program counter to hijack process execution. Now let's head back to our VM and write a simple program to demonstrate this thing. Let's write a vulnerable function which takes character pointer and copies it locally in a buffer, right? So let's call the vulnerable function. The goal of this demo program is to execute the function new func. But as we can see, the main function calls the vulnerable function, and vulnerable function calls printf and a string copy, which I should mention here. Now, if we are able to control the PC or the program counter as we were able to control it in a previous example, the goal here is to call the new function. So let's save it, compile it, gcc simple.c minus of simple. We are not going to compile it as a py because by default gcc compiles as a py now, and what happens is the py, since py contains relative addressing or the offsets into the sections, there are a lot of null bytes. And since string copy is a function which will terminate at null byte, we would not be able to write the whole address of the function. So we are just compiling it as a NoPy. And done. Sorry, it is going to be MR. Too few. Oh, so, okay. We missed something. Yeah, we need to pass it the first argument, the first runtime argument of the main function, so that this gets copied to this function. So Control C, compile, and let's see what happens if we execute this. Okay, hi, done. Hello, segmentation fault. Okay, let's analyze it in GDB. What happens? Let's disassemble the vulnerable function, and oh, it only has space for 4 bytes. Okay, but again, we are, so first thing we are going to do is to put a breakpoint here. So the first thing, yeah, or instead what we can do is, instead of doing all this, we can just run it with a. So let us know what is the problem. Segmentation fault, and by DDDDs we overrode the PC, right? As you can see, we overrode the PC with 4 Ds, and the input was this. So after 8 bytes, the 4 bytes after 8 bytes are overwriting the program counter. So let's see where the uh, function is. Let's have a look at info functions. Which functions do we have? It's taking some time. But this is cat simple.c. Okay, the name of the function is new func. So let's just have a look. Let's disassemble with object dump. Grab new func. Okay, so the address of new func is this, which is 010434. So let's pass this as a argument. Python -c print. We got 8 bytes as junk. Okay, we got 8 bytes as junk. Then the next 4 bytes are going to be written in reverse, which is 34, 04, 01. No, we don't need to write null, but again, yeah. Ignore null byte input does not really matter because null byte is by default there on the stack. So can you do it? And we were able to execute this function. Any questions till now? Last part, what we are doing with object dump and Python. Okay, see, with object dump, I disassembled the binary and found the address of this new function because we need to override the return pointer with the address of this function so that after this function, the execution will go to this function and then exit 0 will exit it, right? Now, I could have done that from GDB, but since GDB takes a few seconds to load, and here when I was trying to find out the address of the function new func, it was taking a little too much time. So I quit the GDB and simply found the address from object dump. Is this part clear? Okay, great. Now, as for Python, what we are doing here is I can write the 8 A's with hand, but I cannot write these bytes by my hand. So what I'm doing is I'm using Python. I'm using Python to write these uh, characters in their hex. So when this uh, gets printed, or rather this gets printed, Python automatically puts these in a proper format so that the return address gets overwritten with this. So is this clear? Okay, great. Any other questions? Okay, let's move on. So now back to the presentation. Now, so far we control the flow of execution. But the question is, what if we do not want to execute another function from the binary, or rather, we want to execute our own shell code, which does something, let's say bind shell or reverse shell, or just gives a plain shell as a local root shell, right? So how to do this thing? Now, for that, we need to inject our shell code along with the input data and redirect the flow of execution, or basically point the program counter to it. just as we pointed the program counter to another function in the previous example. Now let's see how it all works. So you remember the binary from yesterday, which you cloned using from the GitHub, from Ravi sir's session, right? ARM challenges. And yesterday we were at stack 5, not less stack 5, which is, it takes some, it waits for input. We enter some input and nothing happens. So the first thing is to see how to crash it. And once we are able to control the program counter, we will inject our shell code and then move forward, right? So let's open it in GDB. Okay, let's have a look at functions. What do we have here? And besides the main function, there is nothing custom function, right? These are C library functions about gets, and then there are other functions inserted by the compiler. So let's disassemble main. Okay, so main function does nothing. It only calls the gets function and then it exits. But what it has is, it has at least 72 bytes of space, because stack pointer is making 72 bytes of space. So let's just create a pattern of, let's say, 88 bytes, and then use that as an input to the program. So run the program. And it is waiting for the input. It received segmentation fault right here. And of course, it was supposed to receive segmentation fault because uh, only space is 72 bytes here, and we are giving it 88 bytes of input. So the buffer overflow will happen. Yeah, so another thing to notice is that this 72 bytes is not all for the buffer where the gets will store the input. This is 72 bytes for whole stack of this local function. Now we see the PC contains our AAA. So let's see this pattern. Let's clear the screen. Control L. Pattern search 65, 64. Okay, so let's create a string with Python a into 64 plus b d and f. Now this is 72 bytes of string, and let's run the program. Input the string, and it again crashes in base, right? So it takes 68 bytes before overwriting the program counter. So we have verified that thing. Another thing to note is, since we have 68 bytes, so let's Okay, 68 bytes space. Then PC overwrite. And then there's this rest of the stack frame. Now what we have to do is, objective is to execute shellcode. So we can do two things. One would be to store the shellcode or to accommodate the shellcode in 68 bytes and redirect the execution of PC to the start of the buffer so that shellcode works. Or we can do another thing, and that is we can write 68 bytes of junk. We don't really care what this is. This will be PC override, and then write a shellcode here, and we will point the shellcode to this, right? So we are going with the first approach because it guarantees that we have 68 bytes. We don't know what happens after this. Might be some other function, might be something else, right? Anything might happen. So what we are going to do is, first thing is to get a shellcode. Now you can write your own shellcode by your hand if you like that thing. If you want a working shellcode, you can just search shellcode in through. You can search shellcode through this Jeff plugin. Shellcode search Linux. Um, and it tells you there are different compatible shellcodes with this binary and architecture. Now for Linux ARM, we have the following shellcodes. So we are going to use execv to execute the shell. To get a shellcode, just do shellcode get and ID, right? The ID is 904 and it gets written to this file. Now let's have a little look at the maths. The size for the shellcode is 34 bytes. 34 bytes for shellcode. 68 minus 34 is 34 bytes for junk. And we have the next bytes will be PC. Let's quit this and exploit. So this is the shellcode that is from that file. For example, let's just, okay, we are in this. So here's the shellcode. 138FE2 and this is 138FE2 basically, right? So we have 68 bytes available. This is the shellcode. Now junk is, we are going to write knobs because the addressing might change, the environment might change inside the debugger and outside the debugger. So even if the pointer lands somewhere inside of our shellcode, that would not be a very good thing. So what we're going to do is, this is how the structure of our payload will look like. 4 bytes of junk, which is going to be knob-like instructions. followed by shell code, followed by 2 bytes of aligning, so that the next 4 bytes of return pointer is perfect, okay, modified, right? Now this is move R0 in R0, or R1 into R1, I think. Yeah. Yeah, okay, so this thing is, this is the move R1 into R1, which will basically move the contents of R1 into R1, which, as you can see, it will not really do anything. Now 4 bytes of this times 8 is 32 bytes. Then we have some shell code, and then we have this alignment, and then we have this return address. So if we run this thing, Python exploit, it prints it on the screen. So we are going to write this into exploit, and we are going to get, and as you can see, we are able to run commands on the system. So any questions in this? Okay, so we are taking a 10 minutes break, and so you can try it yourself, and if there are any questions, do ask so we can solve those things.
Okay, thank you very much, sir, for this wonderful workshop. And guys, we will meet again after 10 minutes. It's 10-minute break.
Okay.
सो गाइस, आपको सेशन काफी अच्छा लग रहा होगा सर का, ARM एक्सप्लॉइटेशन का। किसी को भी कोई डाउट है सो यू कैन राइट डाउन, एंड जब सर स्टार्ट करेंगे देन यू कैन आस्क हिम।
हेलो,
यस सर, यस सर।
कोई क्वेश्चन है क्या?
नो सर, आई जस्ट इंटरेक्ट विद हिम सर।
अच्छा, ओके, आई वाज थिंकिंग कि कुछ क्वेश्चंस है तो बता देते हैं, कोई दिक्कत नहीं है।
ओके, सो आप क्वेश्चन राइट डाउन कर सकते हो चैट एरिया में, एंड देन सर उनका रिप्लाई दे देंगे।
हाँ बिल्कुल, क्वेश्चंस काफी कम आ रहे हैं, एक्सपेक्टेड अ लॉट मोर क्वेश्चंस।
Mm. Hello, excuse me, sir. Is there anyone listening?
यस आदित्य, यू कैन टेक्स्ट ऑन चैट एरिया।
All right, all right.
Hello, hello. Can you hear me?
यस सर, ऑडिबल
Oh,
सर।
okay, great. So the question is, can you also share some of your experience regarding analysis for RTOS? Unfortunately, I have never worked on RTOS, so sorry, I would not be able to share anything about that.
Sir, there is two more question also added in chat area.
Okay, so here we are. I just wanted to know like what ARM is. So ARM is basically a type of architecture for microprocessors and microcontrollers like Intel is, right? And they also perform the similar task. Now, ARM does not manufacture their own chips as Intel does, but what the ARM does is ARM licenses its design process and other manufacturers manufacture chips based on it. For example, now as for the scope of ARM, ARM started in 1990s, if I'm not wrong, 1990, and then it was initially limited to microcontroller markets. Today, as of today, ARM is everywhere. It is in microcontrollers, it is in mobile phones. Virtually every Android and Apple device uses ARM. Apple has launched, Apple has created their own ARM chip to be used in their own laptops as they were not happy with Intel. So ARM is, as the way ARM is heading, so it is really competing with Intel and might be able to overtake Intel at some point. So from embedded systems to mobiles to routers to computers and laptops, ARM is going to be everywhere. Now, as for the second question, can you share resources to study on MIPS disassembly? Okay, so there are multiple questions. The first thing is resources to study on MIPS disassembly. So MIPS and ARM are quite related. If you understand one, you should not have any major difficulty understanding the other architecture. There are multiple resources on MIPS. I do not have anything on hand right now. So if there is something you are not able to find, just drop me a message on Twitter. I will be sharing some stuff there, right? Vulnerability finding and exploitation. See, in general, there are lots of tutorials on vulnerability finding, exploitation, which are really accessible just from Google search. So if you are looking for something specific, then that is a different thing. But if you are asking for general vulnerability finding and exploitation tutorials, then there are a lot on Google, which you can just find from simple Google search. For example, exploitation of buffer overflow, right? Okay. Now the last question is what fuzzer you use and why. See, fuzzers. So if for someone who does not know what fuzzer is, a fuzzer is an automated tool which provides or supplies malformed input data to a program in hopes of crashing it so that we can find or locate any vulnerabilities which are present inside the system. Now moving on, as for the fuzzer, see there are some very good fuzzers out there in the market, but usually any fuzzer you download from internet is not that good for your specific work. And in most cases, what happens is you end up modifying it either by extending it or either by integrating it in your own fuzzer. So at the end of the day, it becomes a personal in-house fuzzer, which cannot be shared. So I think you got what you were asking for, right? My views on AFL. AFL is nice. Its feedback-driven approach to fuzzing is the best thing. That kind of revolutionized the fuzzing market or the fuzzing uh, groups back when it was released. But now it is not really suited to all the areas, and sometimes you are just okay with not using AFL. It really depends. I mean, if the first and the only thing you used AFL and you are pretty comfortable with AFL and you are able to extend it or to make it work on all types of applications, then great. If not, or if you are working with other fuzzers and you are happy with them, that's also great. See, at the end of the day, what matters is if you are able to do your work or not. Tools do not really matter that much. So recently, Tesla car got hacked by only using Raspberry Pi. Does this have any connection with? It does seem like. I'm not fully aware about the technical details as well. But yes, the microcontrollers in the car, and since these days cars are also connected, it seems pretty straightforward. Now, one thing that I would want to clarify is I have not done car hacking myself, but as far as I know, by seeing other people, cars, since cars have not been that much around in terms of technology as we have computers, so they are quite lacking in the security department. And therefore, in almost every contour contest or in every car hacking village or scenario, there are some car companies which keep getting hacked again and again. So okay, so as for the question about does ARM have vulnerability? See, it depends. I don't know. I'm not that big of an expert on microprocessor design. I'm hardly an expert on anything. But as Intel have vulnerability in its chips as well as the softwares that run on Intel have vulnerabilities, it might be the case with ARM. So far, I have not yet encountered anyone who said or who exposed any vulnerabilities in the ARM design itself. The last thing I heard was Spectre or Meltdown, which were, I think, 1 or 2 years ago. I think 2 years ago. And those were huge, which were in actually microprocessor design. So if you count that, then I guess yes. But see, ARM and Intel are just the platform on which programs run. Not a lot of people design or create those microprocessors. As you compare with, anybody can be a programmer, right? You have a laptop, you can code. And these days with Whitehead Junior and other platforms which are pushing to teach uh, programming to 3-year-old or 5-year-old kids, then yes, almost virtually everybody is a programmer, and virtually everybody is able to or will be able to code applications. But designing and creating microprocessors, that is a very big thing. So only a handful of people do those things, and therefore the chances are, of course, with that much. I would say in that much ratio, because the more people you have, the more software you have, and if the people are not really that educated on the software security, then the more bugs you have in the software. But when you have only one or two or let's say three companies, then there goes your chances of finding bugs in those things. So is that clear? Okay, so any more questions? Did anyone follow with the practical demonstration of the exploit and get stuck anywhere, or everybody was able to do it completely flawlessly and we should move on? My social media handles. Okay, so PawnRap is on Twitter at PWNRIP, and that's it. I keep my other social media separate from my technical things. So if you want to connect, you can connect there. Okay, so shall we continue, or do you want some more? Okay, so here we are, and let's start again. So you can see the screen, right?
Yes, sir.
Cool. So starting in that, now we were able to exploit the stack overflow in the program, and we were able to run our shell code. Now we are moving to format string exploitation. So, introduction to format strings. A format string is a string that consists of format specifiers, which directs the interpretation of input. So, simply saying, a format string has something known as a format specifier, which tells whether the input that will come here is going to be an integer or a float or a string or a character. Now, if you have programmed in C or C++ and you have used the function printf, you have used format strings and you are familiar with the term of format string, format specifiers. So format strings are pretty much used by a variety of functions. To be honest, you can write your own function and use format strings as parameters. But in the standard library, the printf family is one such major family that uses format strings. So a few functions that use format strings: printf, sprintf, vprintf, snprintf, v and vf printf, etc. Right? There are many functions. So now this diagram has been taken from c++.com and it tells you which specifier produces which kind of input. So %d or %i produces or displays a signed decimal integer, whereas %u is used for an unsigned decimal integer. Now we all are familiar with these things. We all have used %d, %u, %o, %x for hexadecimal, %f for float. Uh, then there's this e, g, other things, right? Hexadecimal floating point lowercase. It is expected like this. Then %c is used for character, single character. %s is used for strings. So it will print all the characters in a string as a single entity. And then we have %p as a pointer address. And then %n, which does not print anything, to be honest. Is this clear to everyone? Or should I explain something else? Okay, moving on. Let's understand the format string vulnerability that we have. Okay. So here we go. So we are writing a simple program which takes username as which takes your name as an input and displays it back. Right, very simple. F gets with maximum is 120 from the standard input. So this 120 ensures that the input does not read more than 120 characters, and because that is the limit or that is the size of our input buffer. So no buffer overflow here, right? Now, okay, so printf. Here we're using printf with name. See, demo. So it is working as expected, right? But we have something interesting here. Now here we have used a string inside it, and here we are using printf without anything. So which is basically a string because that is a string of 120 characters. So let's see what happens if I enter something else. So let's say I write this thing, but I write %x. And now it says %x has been translated to 0. Okay. Let's see what happens if I try to do something else. %x, 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 %x. Okay. Now my program is leaking some data. For example, okay, we have for the first %x, there's a 0. For the second %x, we have this. For the third %x, we have this, which seems to be an address from a stack. And this also seems to be an address from stack, right? So this is the problem for not properly using format strings, is that we were able to craft our own format string as an input. And when this format string was passed to this printf, it became that thing. So let's modify our program to include that thing, right? So, okay. And just for the demo purpose, we are using the same string to demonstrate what happens when this string is passed to printf, right? So we are passing this thing here, and now here we are passing it in code so that we can see if there are any differences between the two. And apparently there are no differences. As you can see, I passed this string, right? And here it has this, and then here it has this 09AC2FF0. Now the question is, what are these numbers and where are these coming from? Any guesses why this weird output we are getting? Okay, so no idea. Okay, so the reason for that is, let's make some modification. Yes, it is interesting. So that's why, that's what we are going to see, how interesting it is, right? So let's have a look at the program again. And let's comment out these things. Let's not comment out actually, let's just analyze it in GDB so as to see what is going on. Let's disassemble the main function. And after this f gets, there's this call to printf, which prints our vulnerable things or our custom format string. And this printf prints hello, welcome. This printf prints a vulnerable string, or this is the vulnerable printf. And then this printf prints stuff to the hard-coded string, right? So let's set a breakpoint at this printf right here, break main plus 58, and let's print another at 68. Let's set another breakpoint at 68, and let's run the program. It is waiting for input. There we go. And now our breakpoint has been hit. We are at breakpoint 1, and let's see what the stack contains. So the stack contains this value, and then there are these values. Let's clear the screen for now. Let's print 12 words from stack sp. This is what we have. If I do an ni so as to get the output of printf, we get the output of printf as this. So we can recognize this BEFF714 right here. But what are these three values? Any reason I skipped plus 48? Let's see. Where is plus 48? Let me scroll up. Right. Okay. But plus 48. Where is plus 48? Oh yeah. The reason for skipping this 48 is because this has a hard-coded string. Let me show you. See. So we have first printf, which is enter your name. We have second printf, which says hello, mister. The third printf is the vulnerable one, right? And the fourth printf. And since we are using the same string as the vulnerable one, we need to inspect these two. So let's see in this, the first printf, enter your name, f gets waiting for input. It is the hard-coded hello mister print. This is the vulnerable printf, and this is the printf, which is also again vulnerable, but we have hard-coded our string, right? So is that clear? Okay, cool. So moving ahead, this is where the breakpoint was hit, right? We inspected the stack. This value is the same one, the last one, right? So we have to ask what are these three values, right? So let's see. At this point, 469 cc 100, is it somewhere inside? So 469 cc 100 is R2. Okay, so this one is R1, it seems. This is R2, this is R3. And then this is the first value from the stack. Because this 469 cc 100 is right here, you can see, right? So R2 is 469 cc 100. BEFFF 540 is R3, and 0 is R1. So R1, R2, R3, and then we start seeing things on the stack, which is this one. And now if we continue, we will hit another breakpoint, which is the second printf, actually the fourth in the program, but first was the vulnerable and second one with this string, right? So R0 is again, sorry, R1 is again 0. It is again 469cc100, and this is this value. Let's step it again. Let's have a look at what the stack has for us, right? So the value is same, 714, and the next instruction, it gives us where is the output. I think we are missing the output somewhere. The output must be somewhere around here, and we are unable to see the output. So let's continue this, and here is the output, which was again the same thing, which is BEFFF 714, then 630, 100. Let's see if those are the values. 100, 714 from the stack, and 630 as R3 to the printf. This recording will be on YouTube, so you can always come back and watch this. So is this clear what these %x are doing and where these values are coming from? Okay, cool. So moving ahead, let's quit this thing. And therefore, let's just do this. So the first %x is R1, the second %x is R2, third %x is R3, and now the fourth one is where the stack starts. Let's print, let's say, 4 values from the stack. And these are the 4 values from the stack. 1, 2, 3, 4. This way we can read the stack to some degree, because we also have a limit on how much or how big of a string can we enter here, right? We can only enter 120 characters. So anything beyond that we would not be able to do this through this usual method, right? So another thing that we can do is we can use some width modifiers to make sure we are getting the full output. So for example, we are using 0.8 between % and x so that we can get the values in a proper fashion. So if you see here, we were using %x and it was a simple 0. But now when I'm using %08x, there are 8 zeros. So this uniforms the output. Then we have this, we had this 1, and we have this 7 zeros followed by 1, which is 8 characters. Okay, so that is nice. We have a little bit of understanding about how format string vulnerability works and how we can use it. So moving on to reading arbitrary memory using format strings. So we saw we can read data from the stack using %x. Now there is a problem. The problem is you cannot really use unlimited %x, right? The first problem is you cannot use unlimited %x. Second thing is, what if the data is not on the stack? Or what if the data is above your current value in the stack, and when you are moving forward, because you are moving forward essentially on the stack, so you cannot track back. So there are a few problems with this approach. Now let's have a little demo of how we can read arbitrary memory using format strings. So okay, so this is our program, and as you can see, our goal is to read this password, and let's just add a little check here, string of h. So if the passwords match, we pass, or else we fail. And that is a very simple program. So what we have to do is we have to read this password from memory and then use it. So let's compile it. Let's see. Okay, I failed. That is R1, that's R2, that is R3, and that is stack first variable, stack second variable. And here is something interesting, right? So I have 4 A's as my input. And then what we have is, as the first variable on the stack, or as the first 4-byte chunk that we are able to read from the stack, is these 4 bytes of these 4 A's, which is very interesting because we can use it. So let's load it in GDB and try to find the address of password. Let's say info variables. We have a variable by the title password, which is going to be a bit hard because it has null bytes, right? So let's compile the program in such a way that we are able to use this sequence. Wait a second. Okay. Let's just compile it as a NumPy and see if it works. Okay, nice. Now this binary is working fine. And we have some problem regarding this. Okay, so it seems we would not be able to use this just let me see how it works. Oh yeah, my bad. I used the wrong compilation option. So what I'm doing here is I am setting base mapping address for data section, since my variable, which is this password, is initialized during declaration. So it goes to data section. And since it goes to data section, I have set my data section to this page right here. The reason for that is if I do not do this, the this byte will most probably be a null byte and we would not be able to use the address. Anyways, so let's verify in GDB where we are going. Okay, so info variables, and here we can see, and it has something else as well. Okay, so there are multiple things going on. We have a null byte in the sequence. I think we need to really change this thing. Okay, let's just put it here. We compile it, we load it in GDB. And we need to run this because, sorry, main. We need to run this because the variable is a local variable and it will come into existence when the program is running. So let's see. Let's just password. There is no symbol password in the current. So where is the password going to come into existence? Let's say the password is after this printf plus 26. Continue. Okay, we are going for a different thing. So sure. Okay, so instead of this, for some reason, that is not working. So I had prepared a few different things. So let's start with a different one. So now we are going to have a look at the first format string. Username is admin and password is admin, and it says imposter. So let's load it in GDB and see what this means. str1, what this binary is doing. So we are going to perform a little analysis, considering we do not have a source code. We do have the source code, but let's just not use the source code for this one, right? Let's do info functions. And okay, this binary is a statically compiled binary. So let's disassemble main and see where we get from there. Okay, so this is the main function, right? Coming down, we see we have a mem set. Okay, we have a function. We have got to read password. Then printf f gets probably taking input. Printf, another f gets. So I think the first one is for user, second is for password. And then it is comparing and okay, so let's see what this read password function is doing. Disassemble read password. Okay, so this read password function is opening a file. It is reading some content from the file and it is closing the file. So let's see what this function is reading. So let's, which file it is reading from. Break at read password plus 18, and let's say let's use this 9s plus 34. So we get to know where in memory the password is getting stored. Let's run the program. And it says fopen is getting called with key.txt with a read flag. Okay. So the key.txt file is being read and password is coming from there. Nothing hard coded. Right. Okay. Let's continue this thing. And now we are at fgets, where the first argument is the buffer, right? So it says password, it seems it's only 16 bytes, not even 16 bytes. The last byte is set by default, so it might or might not be the included in the size. Okay, fine, no problem. So let's just say now this is where our password is located and the address is this. So let's find out the vulnerability. Username, say %x. Okay, so there is the vulnerability. It is R1, R2, R3, first value on the stack, and second value on the stack. Okay, so in this case, are 4 A's are stored as a second value as this point in time, and not the first value as we saw in the last example. And the password is, since we don't need to know the password, so we are an imposter right now. Okay, so the goal for this topic for now is to be able to read from this location which contains the password from the file. So what we are going to do is we are going to pass this address in Little Endian 1C 04 0101. Followed by, I guess we have 4 1 2 3 4 percent 08x multiplied by 4. And then the last thing what we are going to do is, instead of using %x which prints the values in hex, let's use %s so that we can read the password. And it will be like this. And then new line. Okay. So the new line will terminate this as one input, which will get us this output. And let's set the second input. Let's just leave this thing for now, right? So let's pass it to fmt str1 and we get something. So this seems like a password. So let's try this password. So fmtstr1, and yes, we were able to. So basically what we did in this challenge was to be able to read from the memory of the program. Now the password was located in another location, and we were able to read what was stored in that memory location. In this case, password was located at address 0101041C, and we passed that address, and since that was a string, we passed %s to read the content. Any questions? Okay, so let's revisit the steps. Now, the first thing that we did was, uh, okay, so let's start from the very basic again, repeat the whole process. We have a rock binary. We have no understanding of what this does. We do not have source code. So let's start with the analysis. It is a 32-bit LSP and stuff, right? Which we don't need. We run this binary and we see it ask for username, let's say admin, and a password. Okay, so it probably is comparing username or password or something, right? It is checking whether we are the correct user or not. So let's see what this file is. So we load this file in GDB. And then what happens is we disassemble the main function, because main is where the things start, right? So what we're going to do here is we traverse the function and see which function the main calls. The first thing we see is memset. The second thing that this function calls is a function by the name read password. Okay, we will see that later. Then we see a printf and fgets, which probably takes our input. So first printf asks for username. Let's hope so, right? We are not really sure, but still. The second printf maybe hello. Third printf something else maybe. We also have another printf, and then we have a fgets, which takes input as a which takes second input, which is going to be the password, right? And then once we have entered username and password, it compares a few things, and there's nothing else after that. There's just a printf calls, so nothing to worry about. Now, what we don't know in all of this main function is this read password, right? So we go ahead and we disassemble the read password. Now, in the read password, we see that, well, as the name suggests, it must be reading password or something along those lines. There's a call to fopen, there's a call to fgets, and there's a call to flows. So it is probably reading a password from a file. Now, which file is it? Let's put breakpoints and analyze what these functions are taking arguments. So read password plus the first thing we are putting breakpoint on 18. The reason for putting a breakpoint on fopen is because we can inspect the arguments of fopen and see which file is being opened or read, right? Another breakpoint that we want is at fgets, because fgets will take argument where the data from the file will be stored in the program, right? So we are going to store the, we are going to put a breakpoint at this address also. And since there is nothing else besides these three calls, so there are no other needs of setting uh, breakpoints, right? So let's run this program. And it says breakpoint 1 hit. And we are at this, right? So right now, R0, which is the first argument, it contains the file name key.txt. Okay, so the program is reading from a file key.txt. And how do we know it is not writing? Well, first thing is it is using fgets, not fputs. And second thing is, as we can see, the second parameter to fopen is R, which is read, right? Okay, nice. So we know where our password is coming from. It is not hard coded inside the program. So we need to read the password after the program has read from the file, right? So let's continue and see where the password is being stored inside the memory. Now what that thing is, we are at breakpoint 2 fgets. Now the first parameter to fgets is the address of buffer where the content will be stored. So let's say 4 words in hex, which is 16 bytes, and it is by the name pass, right? Right now everything is null, so no need to worry about anything. But when we step over this fgets and when we see this, now it has something, right? So let's see as a string. Let's clear the screen. Examine memory as a string at this memory, and we see the content of the file that was read was strong pass. Is this clear? Okay, great. So what we have to do is we have to read from this memory address, because now say if we move to disassemble main, right? So this function read password is called before the program asks for your input, right? Fgets is here and read password is here. So by the time you're asked for input, the program already has read the password from the file for comparison. Now we have two inputs and a password and memory. So the only thing to do is to figure out which input is vulnerable to forward string and then extract the password. So let's see. Now FMTSTR1 username is, let's just say %x. And okay, so since %s got translated into 0, which is basically the value of R0 at this point, R1 at this point. So this is where we will put our payload of format string and read the password. So the password will be reflected in this line, and then we will take the password from this line and put it here, right? Let's first verify whether that is the password or not, which is this one. So see, the password is the same. What we have to do is we have to exploit this bug and get this password. So we are going to, first we have to see where our input is being reflected. So the first thing is R1, R2, R3. Now when we have these three registers, let's say, what do we have here, right? So %x and %x and %x. And these are the three first register values. This is a random value. We don't really care about what this is because our four A's are reflected here, which means if we change this, we will change this value, which means we control this. So we control this. Is that clear? Okay, great. So the question comes, how are we going to translate this? Now, percent %x, okay, I think we need to go back here. So %x, this is the %x. %x just prints a value in hex, unsigned hexadecimal integer. But we do not want %x because that does nothing to us, for example, right? So it is not serving any purpose. But at this point, what we know is we have uh, the address where the password is stored, and it is a string. So if we can use %s to read the string, that would be best. Now for that, we have to supply the address of %s, which is going to be here, right? And there we go. So the address was, okay, we need to scroll back, and the address is, where is the address? This is the address, right? So instead of using %x, we are going to use %s on the address, so that %s, when gets a valid address, it reads a string from that memory. So this is what we did here. We put the address of the string which contains the password, and then since 1, 2, 3, 4, fifth is the parameter, this is the fifth one, which translates this input. So we are using %s here, and enter, we get the strong password. Now we have this password, and we can use this. Now, of course, instead of doing it in two steps, you can do it in a single step by automating, or if you have used pawn tools, you can use it in one go. For example, you can pass this input and then wait for the output, and when the output gets, you read the last thing and then put it as a second input to the program. But here I'm not using pawn tools, just for the demonstration, just for the manual demonstration. I'm using manual approach. Okay, so is that clear, or is there something that I need to repeat? Okay, so with that being done, at this point, we know how to read from any memory location, right? But the thing is, we can read, but it does not change many things. For example, what if the application is not really having anything which you can use, or let's suppose the application has some credentials or something, but again, with reading, you are only able to do what the application can do by itself, right? But what if you can write, or you can modify any location in the program? Now, if you are able to write the value of your choice to the value of, or to the address of your choice, you can basically change anything in the program, which is why we are now learning about how to write arbitrary values to or at arbitrary memory using format strings. Now, if we say %n is the format specifier that helps us to write memory, but it is not as common as we think it is, or actually we do not use %n as much as we use other format specifiers. So by looking at these things, this table, we can see that we have used almost every single one of these besides %n. A majority of us have, right? Now %n does not print anything, as it states, nothing printed. The corresponding argument must be pointer to assigned end, and the number of characters written so far is stored in the pointed location. Okay, so what does this mean? Let's have a little demo of how to use %n and say and demo.c. And now let's print %d. So bytes equals to %d, which is bytes. Let's compile it. And it says bytes equals to 8. So let's have a look at the program. So we have Himanshu followed by %n, and then we pass the address of bytes as argument to this %n, right? And then we print the value of bytes. So at this point, %n did something, and now bytes contain 8. So why this happens is because %n counts how many bytes have been printed on screen and writes that value inside bytes. So now Himanshu contains 8 characters, and since 8 bytes have been written by this point on screen in this printf call, so %n writes that 8 inside this bytes, or this location, or this address of bytes, which is this. So when we print the value of bytes on screen, it says 8. So %n does not print anything, it just writes to a memory location which is provided by us. Is that clear? Okay, great. So this is what we are going to utilize in our demo. So let's see the second one. What this does is, okay, so it is some output. So it asks for my name, and based on that, it greets me. Then we have a hint that this location contains this value, and then it says you lose Mr. Anderson. Okay, so let's see if it is vulnerable. Syntax. Okay, it is vulnerable. Let's see what this program does. Okay, so let's disassemble main, and we do not see any other call. We don't see any call to any other function besides the printf and fgets. Okay, so we have a printf, fgets for the input. Then we have one printf, we have second printf, then there's a third printf. Okay, so it says it is comparing R3 with R2, and it is branching if not equal. Okay, taken. And by default, there is the message that we lose because we are not able to do anything, right? Okay, so what did I check? I run the program as always. I enter my name, nothing happens, right? Now I enter some string and I check for format string. And since %x reveals 0 or anything, I mean, if the string changes and there is a value here, so it is vulnerable. We can go a little bit ahead, a little bit further, and we can see %x, %x, %x. And these are probably this R1, R2, R3, and then that should be something from stack. No idea, right? For now. Now we have seen that this program is vulnerable. Let's see what is actually happening, right? Because it says you lose, so there must be a you win message. If it reads from the stack, yeah, you can say that. I mean, if it is interpreting the format string, which it should not do, then it is vulnerable to format string because you are able to supply the format string of your choice through which you can read content from stack or from memory, as we saw in the last exercise, right? Okay, cool. So the program is vulnerable and we have a message that you lose. Okay, so there must be some comparison of something with something, but it is not telling us what is that. And let's say load it in GDB. Okay, so there we go. Disassemble the main, and the only comparison, if you look closely, the only comparison is here. This is the compare instruction. So let's put a breakpoint here, right? Let's put a breakpoint at 78. So we will see what these two values contain, because this value is a load instruction which loads a value from R7 plus 124 into R3, and then there's a move of this value into R2, and then it is a comparison, right? So let's just put a breakpoint here, main plus 78, and run this. Just enter the name, and here we are. Now it says it is going to load a value from R7 plus 124. R7 is, this is R7 plus 124. Okay, we will see that later, right? So SI. Okay. Now there's this comparison between R3 and R2. So let's see what R3 and R2 is. R3 is 42 and R2 is 539. So, and let's have a little, let's scroll a little bit and see what is going on here. It says this contains 42, and after that the comparison we lose. So let's see what this is. It contains 42, and this is probably the same 42 that is here. We need to make it 539, or which is 1337 in decimal, so that both these values become equal and we pass the thing, right? So let's see how it goes, right? Now let's try this. 1 2 3 4 %08x %08x. This is going to be weird. Let's first find out which value is our controlled string, right? It is 4th, it is 5th, or it is 6th. Okay, so it is 5th one. The first one is R1, R2, R3. It is something, I don't know what this is. And then this is the value A's, right? This is A's, 414141. So let's just okay, so the address is this: B4 F5 FF BE, followed by %08x, or let's just say, yeah, let's make it uniform. Okay, so I will explain. See, this command is examine memory command in GDB, right? And this is the address from which we want to see the contents of memory. Now, here are three things. The first one is a number. Second one is the size, and the third one is format. Which means I want to examine one word. A word is 4 bytes in hex from this memory location, which is basically 1. So are you comfortable now? Okay, great. So we have this value is the 5th value. So we need to make 4x, right? And then we get this, let's just say a %10, and we see this. Now we need to feed this to fmt str2. Okay, so now we have successfully changed the value from 42 to 29. And let's do some calculation. 0x29 is 41, and 5d2 was it 9? That was, I think, 1337, right? So okay, so we need to modify this a little bit. Yeah, so we are right now at this point that we have, by specifying %n right here, so by this %n, all these bytes are total 41 bytes, right? What we need is, we need 1337 bytes. So to do that, what we are going to leverage the width specifiers, which is 08x. So as we saw previously, if we just mention a single %x, right? If it is a 0 or a single digit number, it gets printed as single digit. But if we write %08x, even a single digit 0 is written as 8 zeros. So we are able to control how much we are printing on the screen. And this is what we are going to take advantage of. So from 4 to 3, let's split this as %08x, which is pretty much the same thing, right? So initially we had 4 of %x and then %n. Now we have 3%x plus %x, which is 4, and then %n. And let's see how it changes. Okay, I forgot to add this one of these things. Now we have the same thing, right? 29. Because you see this, I forgot this one. It is missing from here, right? So now we are at the same level, which is 41. And we need to make 41 to 1337 minus 41, which is 1296. And 1296 plus 8 is 1304. So we are going to replace the last one with 1304. 1304. And now it contains 539 as expected, or as it requires, and we win. So we were able to write what we want, which is 0x539 to this memory location, and we wrote it. So basically it was a demonstration of how you can write an arbitrary value, because you control this value, to an arbitrary address, because you also control this address, which is here. You change this here and it gets changed. So any questions? So everyone got it, or do anyone have any doubts? Okay, great. So this is how we were able to control what we were writing. Now, unfortunately, well, we are out of time, so we will not be able to cover this in practical, because I think that will take another at least an hour, which would be a little too much. So let's just have a very high level overview of what the step bypass is. Right. So now buffer overflows. So we already saw how to exploit buffer overflows, right? We overflow. We have overflown the buffer. We control the saved return pointer from the stack, and then we pointed it to our shellcode, which was on stack, right? But as we discussed in previous topics about the mitigations, usually there are multiple mitigations on by default, which is one of which ASLR is by default on. DEP is also by default on. So DEP is the compile time protection, which you have to specifically disable if you want to make your programs execute from the memory sections or areas where there is no execute protection permission. For example, stack or data section or PSS or heap or any other thing, right? Besides the executable text section. Now dep is, as I said, it is on by default. ASLR is on by default. Rel row is partial by default, right? It is not null and it is not full. So there are three modes of railroad. Dep is either on or off. So let's see how it affects our exploitation strategy, right? So a quick demo of how dep changes things. I don't think we would be okay. Demo.c. So it is by default. Sorry. So this program was by default compiled with uh, dep, and let's see what happens. So first we need to point it. First we need to corrupt the return address pointer, and then we need to point it to stack for execution, right? So let's just see how it goes. Okay, disassemble function1, break 24 so as to get the address of our buffer, and then break the last one at 34 just before jumping to corrupted return pointer. And now we run the program. It is asking, it will print a few things. Okay, now it is asking. Okay, it is waiting, right? So this is where the input will store. So let's print 4 words in hex from this memory address, which is where the program will store our input data. And then let us print. Okay, so what if we use this address as a return address, python -c print. Let's just use C4. 4 bytes for the space, 4 bytes for this, 4 bytes for this. This is the return pointer override. So for 4. And then we are going to override the return address with the starting address of buffer, which is this one, demo. Let's use this as our input because we cannot input this by typing from keyboard. Okay, nice. So this is what we have. Let's examine a string from this, which contains nothing. But if I continue this and examine it again, it has our input, right? So let's examine 4 words in hex from this memory address, and you can see the return address has been overwritten with the same address where our data is or where our string is. Now, okay, if I use disassemble, we are at this and examine 2 words in hex from stack pointer, first one, the second one, which is this value will go into R7 and this value will go into PC. So SI. And now you can see that PC is this BEFF5C4, but it has not executed anything. It just points to this, right? Now, if I examine the instruction at PC, it is a subtraction instruction. And if I try to execute this instruction, we get a segmentation fault, which you can see here. Okay, program received segmentation fault. This is because we are at this memory location, and let's see the virtual memory mapping for the program. Now the PC is BEFFF5C4, which is this one stack. And the stack has only read and write permission. There is no execute permission here. Since there is no execute permission here, we cannot execute any instruction from stack, which is our shell code. This is what depth is all about. Do you understand? Okay, great. Now, okay, moving on. Here we have now depth bypass strategy. We confirmed we cannot execute our payload from stack. Depth does not allow execution of content from executable memory. But the thing is, we can still corrupt the stack. We can still write any value on the stack. So how can we get a shell if we cannot execute anything from the stack, right? Now this is where return-oriented programming comes in. ROP works on the very simple fact that we can still control the program counter. As you can see, we controlled the program counter and we pointed it to the stack. So we control the values on stack and we control the program counter. Now, since we cannot, since we control the stack, we in turn control the program counter because it is saved for returning to the previous function once the current function finish execution. The idea here is to find gadgets and use them to control execution of a process. Now the question comes, what is a gadget? A gadget is a sequence of instructions followed by a return statement or a pop PC statement or instruction in the ARM context. Let's see how to find ROP gadgets with Ropper. So run Ropper. Load the file. Nice. So the file has been loaded. It has identified which type of file and which architecture it has. To search for gadgets, it has already searched for gadgets, and we just need to run the command gadgets to display all the gadgets in the binary. And these are the gadgets. It says 46 gadgets found. So as I said, a gadget is a sequence of instructions followed by a return statement, which is basically a pop PC, right? Or something else. For example, PX. So if you control the contents of LR register, you can directly jump to it. Or if you control the contents of R3 register. Looking at a few more complex, there's a NOP instruction, there's a POP instruction, right? There's a POP R3 PC, POP R7 PC, and the whole idea is to stack these gadgets on top of one another so that at the end of the day, the function you want to call has its argument in proper registers, and you can call this. Well, unfortunately, we would not be able to cover this scripting ROP chain to bypass depth. So thank you very much. Any other questions? thank you for attending the presentation.
Thank you very much, sir, for this wonderful presentation, wonderful workshop about advanced ARM exploitation. And guys, you just uh, comment on chat section about the feedback of today's session.
Yeah, so it would be great if you share the feedback.
Thank you very much, Himanshu sir and Ravi sir, for this wonderful workshop.
Okay, so there is no feedback yet. So I think we are done.
थैंक यू वंस अगेन सर। और यूट्यूब पे इसका कंप्लीट रिकॉर्डेड सेशन है, वहां पे जाके बिसाइड महाराष्ट्र यूट्यूब सेशन में आपको मिल जाएगा लाइव। और वहां पे भी काफी ज्यादा पार्टिसिपेंट ज्वाइन थे, और सर वहां से भी काफी अच्छा फीडबैक मिला है सर। थैंक यू वेरी मच सर, हिमांशु सर एंड रवि सर ऑल्सो।
Thank you. So thank you for organizing this, and we got a chance to share as well as to present ourselves. And we hope the attendees learned a few things. And if anybody have any questions, they can just contact me, drop me a message on Twitter